So I have sort of a question for Michael Rossman, who invented partiality, as we all know. We're sort of continuing the discussion we were having with Wolfgang Brehm. It does make sense, I agree, to calculate partialities before doing this sort of work, but you run into a problem that you're dividing by the partiality in order to correct for it. And we all remember Nick Sauter's histogram that has this gigantic peak at 0.
Yes, yes.
So how would you propose dealing with that?
I guess I ought to ask Nick a few questions first about those diagrams he presented. He got that average, except in one case, always going to 0. To me, this suggests that he was indexing and therefore taking the intensity of reflections he shouldn't have been taking. That's to say, he was using too big a mosaic spread or too big a beam divergence, and he was getting hold of reflections which should be there, but it isn't because the mosaic spread is less. Therefore, everything goes to 0 because he's got so many of these reflections out measuring them where he shouldn't be measuring.
I agree with that, right? So one aspect of that is metrology, so that the tiles are really in the wrong place, so we're measuring zeros.
Yeah.
The other one was related to the question of mosaicity, that if I choose the mosaicity too large, then I'll be predicting a lot of spots that aren't really in the diffraction pattern. But what we found, and what I alluded to in the talk, is it's not enough just to use one parameter that describes mosaicity. You need at least 2 parameters, one for mosaicity and one that describes the domain size of the coherently scattering mosaic plots. And the 2 of those can interplay, and you can get better fits. So what do I mean by a fit? I mean that the set of predicted spots matches the set of observed spots better. But those 2 sets aren't always they're not going to overlap 100%. So there will be some, like a Venn diagram. So predicted spots in one circle and observed spots in the other circle. And the intersection is what we want. But what goes into the histograms that you were saying is the set of predicted spots that aren't really in the observed data. And I guess...
So, James, what was your question then at first?
My question was, what do you do with 0 partiality spots? I mean, it's easy to, okay, if it's 0, it's easy, you throw it out. But what if it's 10 to the minus 38?
Well, in the original programs which I wrote, I think I had some limits, something like 0.1 or 0.2 partiality. Anything which is less than that, calculated less than that, I didn't use in my data.
Yeah, I think I would do the same.
And then if you did that, those plots of yours would be more reasonable.
No, they would be just be cut at 0.1. It would just look the same way, but they would be cut at 0.1.
No, not the intensity.
It's not cutting them by intensity, it's cutting them by partiality.
Okay, so they would be... Yeah, okay.
Right, I would say the only time that I can remember that those histograms started to look reasonable was with the James Holton simulated data.
Therefore, you should never believe simulated data.
I'll make it harder for you next time.
This is an interesting point. In Wolfgang Kabsch's latest paper on NXDS, he has the same cutoff. His cutoff is 0.7. So he requires the reflection to be 70% there. And this is really high.
Yeah.
And he has, in his model, he assumes the Ewald sphere is thin and measures how far the reflection is away from Bragg. So it's just a one parameter thing. It's not like a volume-based thing. It's really just...
Well, he assumes a spherical relevance.
Yeah. So there's now a simple function between distance from Bragg and quotes partiality, this 0.7 thing. And if you just cut that off, this I think looks very similar to what was done right in the very early the Rick Kurian Optics Express paper, which had this thing called the integration domain size, which is how close an individual pixel had to be to Bragg before it would be added to this integral.
Yes.
And I wonder if this is related. So having this cutoff in that case is really similar to just reducing the size of this domain.
So Kapsch's paper was really an attempt to deal with stills when the crystal isn't moving in relationship to the XFEL data. And so he was thinking about all these problems.
I think he did the treatment correctly in that he was doing what I thought he should be doing. And what disturbed me very deeply about that paper is that signal to noise is still horrible. It's taking a factor 3 hit by using NXDS versus XDS.
It's for synchrotron data.
For synchrotron data. Admittedly finely sliced.
Are you saying that Kapsch treats partiality, or the extent of reflection as a ratio of areas, not volumes?
Yeah, he seems to be doing that.
I'd be interested in if you'd expand on that point a little bit. You're saying that if we're only considering one mosaic block, then we should, the fraction of reflection that's important is the ratio of areas, not of volumes. But if there's many mosaic blocks, it's the ratio of volume. Is it easy to explain why that's the case?
I think it's going back to the Bragg-Roxalt paper, where it's not so much the sum of areas or a volume, it's the ratio of what you get for a particular HKL versus a reference HKL that's always on the Ewald sphere. Now, I tried explaining that by calling it F00, since that's a convenient spot that's always on the Ewald sphere, but F00 seems to scare people because some of us don't believe it exists. So if you can imagine another spot that's always on the Ewald sphere, that's the reference. And you can still integrate over it. If you integrate an area over angle, then that becomes a volume. But it's a volume modified by a Lorentz factor that has to be accounted for. You actually get the same thing with arranging a three-dimensional diffraction pattern. You still have to scale and warp these pixels somehow. And whatever it is you're doing to those pixels, that actually is a Lorentz factor. So you have to do that right. You can never really escape it. But it is a matter of doing the geometry.
Could you explain that a little bit? Because I understood that Lorentz factor is a velocity or a ratio of velocities. What does that mean when the crystal is still?
Well, there's a different Lorentz factor for different geometries, and it was never actually defined very well. Lorentz never published it. But there is a different Lorentz factor, for example, for powder, which is different from that for the rotation camera.
Right, and there's also one for Lowy.
Then there's a different one for Lowy. So the Lorentz factor, the best I can tell, is defined as the trigonometric component to the geometric correction. So there's other geometric corrections like the rotation velocity. But if you want to just lump all that into one thing and say global Lorentz factor, that's actually what we're talking about as a partiality. It's the ratio of a given spot's intensity to what it would be if it were always on the Ewald sphere. It's not technically not a Lorentz factor, but that's actually, I think, what we're talking about. But it's counterintuitive because if the spot's always on the Ewald sphere, then its volume never touches it. It's just the great circle in the middle. So if you have a geometry that always keeps a spot directly on the Ewald sphere, then if you're talking about partiality as a volume, then it's always zero. And that doesn't make sense. Unless you initially take the sum of all the areas over all the Ewald spheres, and then for a given spot, the sum of all the areas over all the Ewald spheres, all wavelengths, all directions. It's easier in my mind to think about it as, to think of the dispersion as a list of wavelengths that are discrete, rather than trying to think of it as a continuum, because then you can always approach the continuum through having enough. And if you do it that way, then you're actually summing areas. And the sum of a bunch of areas, times some, that's just calculus. Fundamentally, it starts out as an area.
But James, that's okay if you're dealing with the variation in mosaic blocks. But what about variation in wavelength? You cannot think about the wavelengths being one unique wavelength. Obviously there has to be a dispersion of wavelengths always.
Yes, you can.
And that gives you a thickness in the other direction, perpendicular to the surface of the Ewald sphere.
Yes, and you can treat that with arbitrary complexity. There's always a central wavelength.
Yeah.
And so that's one. That's one. You can think of that as one Ewald sphere because the wavelength is in fact a number that has to be written down. And that corresponds to a sphere that is actually infinitely thin.
Yes.
But if you have two Ewald spheres, then that's a bit closer. If you have three, then there's closer. If you have a million, then that's pretty close to a continuum.
The wavelength spread will give you sort of a Gaussian distribution about your central Ewald sphere.
Yes.
But I think
Not with the Sauter spectrum.
Yes. Yeah. It depends on your spectrum.
So when I started doing these simulations, I started trying to do this. I had about 10 wavelengths that have the bandpass that LCLS is supposed to have, and the images didn't look any different. And that told me that what was going on is the mosaic spread is just blurring it out anyway. So we're not really, and that's probably why it's not being, that's why the detail of the SASE spectrum isn't right.
But what about the two-color experiment that I showed where you can actually separate the Bragg spots from the two colors?
You can separate the Bragg spots, but they have different partialities, don't they?
Yes, so if you looked at the very high resolution limit, the Bragg spots no longer came in pairs.
The excited difference with it.
We actually predicted that before the experiment started. We simulated and saw that you could divide the reflections into three categories.
But you can do it at a synchrotron. You can take a diffraction pattern with one wavelength and then don't read out the detector and change the wavelength a bit and take another shot. Or you can sweep the wavelength during the shot and make basically simulated pseudo-Lowy experiments. And we did those with in situ diffraction. And yeah, it actually looks like what you'd expect. But the problem is, again comes down to the partiality. It's this 100% error that's seems to be really, really angular dependent. That's what's got me worried.
The delta EV in two color was 100 EV?
Yeah, it was about 95 or 100.
Yeah.
But it's definitely the case that for a rotation camera experiment, you can't tell if you're using silicon 111 or silicon 333. Right? It doesn't really change the result, even though the difference in bandpass is a factor of 14.
It just means some other error is bigger.
Yeah. Well, and also in rotation camera, you're integrating over it. And that was the genius of, well, Bragg, I guess, was that by integrating over the shape of the spot, you don't have to worry about it anymore. So I think if we could model the shape of the spot, maybe not just with one Gaussian, but several.
So would you expect better integration in the nanofocus chamber where the focus is this rather than 10 meters and therefore the convergence angle is a little bit steeper?
Yeah, I think actually Michael's original profile fitting actually took advantage of the fact the beam was divergent. Because the profiles were not rotating around the beam like you'd think they should with the high mosaic crystal. They're actually coincident with the X and Y axes of the detector. And that worked better. Because if you look at those images, they actually are little bars because the beam's divergent.
But it's a different problem on an X-ray laser because the cone is coherently filled. So you have to add, if they're very small, you have to add the displaced shape transforms for every coherent component of the incident beam cone. So
yes, but
then it gets complicated.
But if the beam is smoothly filled in phase space, and if the divergence is smoothly varying from one end to the other, that's effectively integrating over angle.
Yeah.
I agree, but the question rises to whether you add the complex amplitudes or the intensities of the detector for each component plane wave in the incident cone. And the new feature with the XFEL is you have to add the complex amplitudes, not the intensities, as you would probably on a synchrotron.
So I wrote...
So you get different patterns.
I wrote Nearbrag to do that.
Right. And
the patterns actually don't look different. What you get are fringes that are so closely spaced that they're much, much smaller than a pixel. If the features are that close together, unless I'm doing it wrong.
That raises the question which I asked you, John. You gave your talk about what power one should use in relating the intensity to the structure amplitudes. Structure amplitudes, of course, is what we want from the intensity. And we now, with these very small crystals, probably never have a single mosaic block, but maybe not very many. And if we have a single mosaic block, we should be using the first power.
Yes, that's
and
correct.
if it's many, the second power.
It's the Fraunhofer equation. It is the Fraunhofer equation. What I'm calling the Fraunhofer equation.
Yes, absolutely. Yes.
I would use that, but I go back to this point that the concept of partiality, it becomes in this iterative loop where everything depends on everything else, and you're doing multi-parameter optimization of cell constants and wavelength and other parameters to find the partiality, and assuming not a rocking curve. We should reserve the word rocking curve for perfect crystal. An angular profile for the spot becomes so cumbersome, that whole mathematical apparatus, that I think for small crystals it's much better to just treat them as a single particle. That is, as a crystal with a few hundred molecules on a side is like a virus, and to phase it iteratively and reconstruct the entire object, then you will get peaks at the Bragg positions, and you can use them to align and merge different data. It's more trouble than it's worth to think in terms of partiality for a coherent diffraction from true nanocrystals.
I would go so far as to say the rocking curve shouldn't be used for things that aren't rocking.
Well, that's a concept for a different problem. Malkus.
But I mean, we're getting a mixture of these two things, of coherent and incoherent.
Yeah.
And our record is the intensity. How are you going to interpret this? I wonder whether some of our systematic errors are because we should be taking an intermediate power in, because it's a mixture. But this has not been done as far as I know. Where everybody takes the square root.
I've done the calculations. And with
what you've got depends on the number of mosaic blocks you've got in your crystal.
Well, I showed a picture of mosaic blocks in real space from cryo-EM.
Lovely
That's
picture.
the first time they've been seen. And they were 250 angstroms, which is pretty alarming. I mean, I would have thought they're much bigger than that. But of course, it depends on the crystal.
Yeah, if the virus crystal won't be bigger than 250 angstroms, that's smaller than the virus. But this, I think, is a very important problem, because if you take the square root, it makes a lot of difference.
Yeah.
In my simulations and calculations, at least, I've been highly unimpressed by coherence. It doesn't seem to actually change the diffraction pattern all that much, if at all.
Well, no, they're actually identical if
you have a point source.
If you have an illuminating cone and a point in that is conjugate to a point in the detector, it doesn't matter. The coherence between adjacent points in the source never enters the problem, unless for an infinite crystal where you have plane wave to plane wave. If you have plane wave coming in makes plane wave coming out, then coherence doesn't matter, because it's point to point. And coherence is all about interference between overlapping. So where it matters is where the crystal is so small that a plane wave coming in gives a blob on the detector, and then an adjacent plane wave coming from a slightly different direction makes a different blob which overlaps, and then they'll interfere in the coherent case and not in the incoherent case. So it's a combination of how big the crystal is and the coherence at the source.
Do you have a sense of where the crossover is?
No, I think that's actually.
I've got a diagram of where the crossover is.
That's probably the best summary of this whole day's work would be, where is the crossover? If you understood that, you'd understand everything.
It's at 3 microns.
But it depends on the size of the beam.
Yes.
If the beam is small,
Each size, yes.
it's not just the crystal, Jay, it's also the beam.
But how many blocks are there in the beam?
Right.
Are you saying that the block has to be 3 microns, James?
I'm saying that the block is 3 microns because that's the transverse coherence of the beam, with a detector at 100 millimeters.
No, but you could have a 3 micron. Say that again.
If the transverse coherence depends on not just the distance to the source, but the distance to the detector.
But you could have many blocks in the transverse coherence or one, and they'd give you
yes,
a result.
but then they still add coherently. Doesn't matter if they're mosaic blocks or not.
A different pattern.
What it looks like is if you have 2 different crystals within the coherence length, what you get is the sum of those 2 diffraction patterns with fringes.
Yeah.
And the fringes are, the distance of the fringes is the distance between the crystals. So you actually just, between the centers of the crystals. So as the crystals are becoming basically in contact, the fringes become much sharper than a pixel, and you just integrate over them. And when you integrate over them, you get I squared, or you get F squared.
Well, another question I'm curious about, which goes back a little bit. Another question I'm curious about, which goes back more to the question of initial partiality guesses. So taking crystal parameters, beam parameters, and a partiality model and getting out partialities without doing any refinement. So,
and also can include dispersion, can include the spectrum.
Right, so all the things you want to model in the middle, but without doing any refinement of those parameters. It sounds like what Wolfgang mentioned at the end of his talk is that if you try and apply those kinds of things, you get worse results than just taking the raw partial intensities. And that's also been our experience. I was wondering, And a reason why that could be is that the initial accuracies of these orientation things are such that your actual first guess corrections are worse than your partial intensities. But I was wondering if that was sort of the experience across the board, and if that made sense, and what people thought of that.
For simulations, I found the initial orientations are very good.
Yeah, that's what I thought was interesting, because you had that curve where you saw that 0th one worked, but with real data, I've never seen that. I've seen the opposite.
So whether this stands for practical experiments where you have dodgy detector geometry and dodgy everything, I don't know.
So I'm not sure I understand, because I took James Holton's simulated images and I indexed them, and the agreement with the known orientation is dismal. It's, anywhere between 0.1 and 0.5 degrees.
That's the orientation of the crystal.
Yeah, it's the model versus what you know as the truth.
Yeah.
It's very bad.
There's something wrong with your program?
What?
Something wrong with your program?
Well, it's what I showed before. If you base this based on spot position only, then you'll have an uncertainty in the rotations that are perpendicular to the beam.
Absolutely.
X and Y.
Yeah.
So if you include the little fix that I said before, then you can get the orientations down to 0.02 degrees. But still, no better than that.
Not 0.006.
No, not 0.006.
What you could be doing, for the simulated data is, in my view,
that's the width.
something like a post-refinement. Just make the correlation coefficient to a reference and increase the parameters until you are there.
Right. So, it's looking at the known intensities based on a reference. So we didn't do that, but that would be post-refinement. That's based on intensities.
I think it comes back to my original question. Okay, post-refined it, you calculate your partialities, but when you divide by your partialities, I guess we're deciding we're cutting it at 0.2.
But this is easy. You just have to divide your error as well with the same number.
Yeah, so you end up with spots that have huge error bars, I guess.
Yeah, and those will, if you treat the errors correctly, they will not contribute.
Well, taking that to the next level, though, if you have big error bars, that means you need a lower weight.
Yeah.
And the weight is basically the inverse square of the error bar, which means that averaging these things is equivalent to squaring the spot intensities first, or fourth power. Is that right? If you're doing a weighted average, and you're merely dividing by 0 with your...
I said, apply a weight of 0 if the calculated partiality is less than 0.25.
Could be, yeah. Sounds about right.
Now, your suggestion is similar, just to have a more accurate weighting, not 1 and 0, but...
There's something I found in numerical recipes called a Wiener filter.
Yeah, that's good.
And it's where if you think you know what the signal looks like, then you multiply the data by that function. And that's the optimum weight.
Probably it's not way to do it.
So then you're multiplying by the partiality and not dividing.
For weighing, yeah.
But
nice way to think about it.
My drawing of the coherence length mosaic block thing is if you have a line of atoms, well, like this, and an X-ray beam that's a plane wave, you got these two waves coming in and they scatter off of atoms and eventually hit the detector. There's going to be some distance along this infinite line of atoms when you're kind of getting out of the beam, where the distance from here to here becomes half a wavelength longer than this distance. Then you're getting destructive interference again. And so you can do that. This is starting with 10 atoms, and this is the spot shape here. It's 50 atoms or half a micron long. So this is 1 angstrom radiation detector at 100 millimeters, and the atom's 100 angstrom spacing. And you get these, nice sync functions, which grow in intensity up to a point. And once you get beyond about 300 atoms or 3 microns, then you get more and more funny shapes. And even though the integrated intensity is still proportional to the number of atoms, the peak height spreads out.
And so the peak height will actually rise to a point. So this is now the peak intensity of photons per unit solid angle. That rises until you get to 3 microns, and then it levels off. But the integral is flat. It's the same for all these guys. And so I call this mosaic spread, if it's bigger than that coherence length. I call this a B factor because, and this is the disorder within the coherence length, is the Debye-Waller factor because it's interfering constructively. And this curve actually is known in physics. It's called a Mie scattering curve, or M-I.
M-I-E.
Yeah, right, M-I-E, Mie scattering, which isn't normally at this wavelength.
Aerosol's visible light.
But this is the Fourier transform of a line. So I liken mosaic spread to this. So this is mosaicity on a different length scale, where the sun should be a disk, but because it's reflecting off a surface that's not perfectly flat, it spreads out. And even though you can't actually tell, you can actually tell how the wave heights from how much it spreads out over the globe. But actually, historically, Darwin originally proposed this, that there would be slow, smooth variations from one part of the sample to the other, both in unit cell size and orientation. But he decided that was mathematically too difficult to handle, so he broke it up into blocks. This made it piecewise linear, which may have been a new idea then, but it's not now. And it was Ewald who called it a mosaic. And because he liked the mosaic paintings, he thought that was a nice way to picture it, and the name stuck. But a very excellent question a lot of beginning crystallographers ask is, what is this stuff in between the blocks? And the answer, I think, is there isn't anything in between the blocks.
Well, what is the cryo image?
Well, yeah, you can have grain boundaries.
Low angle grain boundaries.
But if you're within the coherence length, then all you're doing is creating a distribution of atomic displacements by rotating a block.
Yeah. And if this is inorganic crystal, there would have to be a low angle grain boundary consisting of a line of dislocations. So the question is, have the dislocations been seen?
James, can you go back to, I think, your first slide where you showed the line of atoms, the parallel instant beam? There we go. Now, a top ray goes off at a bigger angle to the instant beam than the bottom rays. Would that necessarily have the same intensity than the ones at the bottom? When you did your simulation, maybe you should have reduced the intensity of the sideways things coming. You did?
Yeah, let me show you the simulation. It's kind of cool, particularly for the students. This is a Gedanken experiment. Where just take your 2 atoms that are each scattering a plane wave, and we know that they make an interference pattern on the detector. And
Young's experiment.
This is the Young double slit experiment. Now, what Near-Bragg does is you define where your source is, you define where the atoms are, you define where the detector is, and it just draws straight lines, and the scattered waves fall off with the upper square law. But you can also do this. You can actually move the detector so it's in contact with the atoms. So you can imagine if you had some, and you can set the pixel size to be sub-angstrom if you want. So somewhere between, and if you do that, you get 2 dots, right? Because there's 2 sources of light that are touching the detector. There's no interference pattern. So somewhere between here and over there is where the Fourier transform happens. And I think it's instructive to see what that looks like. So here we are. This is our detector with sub-angstrom pixels. That's to scale here. So these are 10 angstroms apart with 1 angstrom radiation. And you start moving them away from the detector. This is the pattern you get. And so you start seeing these fringes. And where you see a fringe is where the distance from this atom to the pixel back to the other atom is an integral multiple of wavelengths. If it's half the number of wavelengths, then they destructively interfere and you don't get any light. And as they move further away, this is still a scale, so they're on the screen now. There's actually 20 of these because it's 10 angstroms and 1 angstrom radiation. Once you're far enough away, then you've got your interference pattern. And that's because, and you can measure the distance between these things and tell how far apart the atoms are.
And these will concentrate into Bragg spots if you add more.
If you add more, yeah.
Atoms.
So this is 3 atoms. Not necessarily ordered correctly. But this is where I try to point out to people that the reciprocal space isn't really a reciprocal space at all. It's an angle space. It's just convenient to think of it in ampersand terms, but it's actually an angle. It depends on detector distance. So this is simpler: 1 atom, 2 atoms, 3, 4, 5. And
these are the fringes we actually see.
Yeah, those are those fringes.
At the XFEL that I showed you. But there's n minus 2 of them for n atoms on a side. It's also important that the intensity goes as n squared, as you were saying.
Yeah, if you look at the intensity here, see that's 1, that's 4, 9, 16, all the way up to 9 or so. And that is the sync function, which is implemented in fast Brehm. Just doing that.
Dinner.
No, not yet. Soon.
No, wait, one question for you. So you said before that we should be treating the nanocrystals as single particles, but the same errors that prevent us right now from applying the partiality model, wouldn't they be a problem for if we were to treat them as single particles?
Well, they arise in different ways, and you would still use the Bragg peaks as the line. You would index them. You would identify the Bragg peaks and then align, use them to assist the alignment. The algorithms that have been developed with single particles are very powerful, and I think it's just a simpler, more elegant way to go.
Yeah, I think so too, but I think they will have the same problems.
They'll appear in a different form.
So would you think that crystal to crystal there'd be different mosaicity, and that would...
This is for assuming no mosaicity, where crystals are 100 angstroms.
What about crystal to crystal, different symmetry, different unit cell contents, stuff like that?
They won't work, can't merge it. You get different patterns.
To a certain extent we have. You can have a given symmetry plus some NCS exists in a continuum up to a higher level of symmetry. You do observe this sometimes. So how do we apply these kinds of methods? How do we deal with these issues?
What the interpretation of the result is a periodic average. So whatever sense you can make of that.
So what do you mean by that?
A periodic average, I mean that you have to construct a lattice to add a unit cell of all of your different crystals into this strictly periodic lattice and form, into a single unit cell and make that periodic, and that's the definition of a periodic average.
Mm-hmm.
I think it's very important, this idea that if you have a converging beam which is filled with plane waves, there are two cases. The plane waves which fill the cone converging onto the sample can be coherently related one with another or incoherently. If the crystal is large and perfect and there's no mosaicity, the resulting diffraction patterns are identical because each plane wave coming in produces another plane wave coming out, which makes one point on the detector. An adjacent plane wave incident cone makes a neighbouring point on the detector, and they don't interfere because they're points. And they're points because the crystal is infinitely large and perfect. So it's only when you confine the crystal that you get different patterns. As James has said, they may in the end turn out to be true.
If the source is really far away, it's really hard for the beam to not be the plane wave.
Right, but plane wave in, plane wave out gives results independent of coherence.
I think with the single particle algorithms, I think they almost, without exception, assume that the Ebot sphere is very thin compared to the object's weakness, which in this case means that fluctuations of density is a physical state. And it wasn't clear to me until recently that that was the case with crystallography, because the physical space blobs of density that we observe are very small. That part we know, but whether the thickness of the Ebot sphere is small compared to that means that wasn't clear. I think now it is quite clear now. A couple of reasons. First is that you can see in Anton's paper in Lorentz showing the 3-dimensional emergence of space. And if this sphere thickness was large compared to the slots and there's should get larger as you go out into space, and they don't.
If we think of something like the NCR, then it's based on a model which initially can be random. Now, we generate from the model a candidate pattern to match with incoming data. The generation of a pattern can be as complicated as you like. It could include all kinds of variables. It could be polychromatic. No one's actually done that. It's a very scientific in principle.
So then that is a partiality.
Yeah, the key point is to compare with the model. That's what makes this efficient.
Well, using the 3D merge approach, you can actually bootstrap the orientation problem nicely, because the indexing gives you a starting guess. And then you just need to do these little tweaks around and see where the measured 3D intensity pattern matches the model. And it's interesting because you can run that a different way, and you can take this 3D model and take a slice out in exactly the same reciprocal lattice orientation and have a look what this look like. You usually see more spots in the extracted pattern than in the real data, which says something about the averaging effect, maybe over bandwidth or over other effects in there. But you might still be able to orient.
The point is you're always doing forward calculation for a model, rather than inverted.
Right, but rather than having a mathematical idealized model, in that case you're actually using the data itself to generate it.
Yeah, okay. What do you mean by 3D calculation?
Okay, so the way the single particle people deal with diffraction, it's like what we did in the pyramid paper, is you take your intensities as you measure it on the detector, and if you know the goniometer, you put that intensity into three-dimensional space. The single particle people don't know that, so they'll try and do expectation maximization to figure out where it fits the best. But here we have an indexing result, and you take your intensity distribution, actually place that intensity distribution into a three-dimensional box or grid. Okay. And that's sort of a three-dimensional method. No, not just the variance box, the entire detector. The entire detector.
In general, it's diffuse scattering from the entire object, including its boundaries. And then you phase it intricately, which is rather like density multiplication.
When you wrote a program for doing this on rotation data, do you scale the intensities anyway and set them in form and make the sector photos out of oscillations?
I think this was for rotation data. So it seems that it scales over 1.
Okay.
But they're all different sizes, man.
Yes. Well, of course, when you merge it up, you don't see fringes anymore because they've all been washed out. But you do see the residual streak of intensity. So for catex and B, it's interesting you see these streaks that go along parallel to faces, which is nice. We had a look also on lysozyme, and it turns out that the faces form in a different way and you get diagonal streaks, which is interesting. So it's very much an determination.
You get the shape of different.
You can tell what direction the faces are once you switch the whole thing. Yeah. Oh, we found it out. We went, now we know what's going on here. That's important, isn't it?
Before we finish up, can we have a really quick discussion again about what we can use as a measure of quality? Just to remind you, we said CC half was precision, not accuracy.
What number to chase?
Right, what number to chase. But then if you say accuracy is defined by having a model, then we could say R3 is accuracy. Can we combine the two or just always mention two? Discuss.
I'll put
Someone else go first.
My vote is my vote. And this is it's very much inspired by discussions. Yeah, I work for Brehm, so I'm not sure if this is this is very much inspired, if not directly from him. But I don't want to put words in his mouth either. Is that the gold standard is if you're doing molecular replacement is leave something out of your molecular replacement model. Do an emit map, look at that particular bit of density for which it's impossible for there to be any phase bias because it was never there, and look at the quality of that. As Nick suggested, things like looking at the strength of a metal peak or anomalous peak, something like that. So that's kind of, I think, the gold standard is the only one which we can really convince ourselves that there is no potential bias. A big challenge with the statistical metrics, particularly the overall ones like CC1/2, is if we're moving into a time when everyone's going to be doing post-refinement, which I hope in 6 months, a year, we all will be doing, there's a big challenge in terms of CC1/2 is extremely tightly coupled to all the post-refinement targets. Post-refinement essentially says, here's the intensities we have, here's our average or model intensity, let's try and jiggle around the crystal parameters and beam parameters such that these agree as well as possible. Well, of course your CC1/2 is going to get better, it's your target. So this is why we must look at electron density, or in the context of post-refinement, a cross-validation approach.
What do you...
Sorry, but is there, I hate to simplify something complex, but is there a number with which we can summarize the quality of this emit map?
Okay, ask someone better at this than me.
So maybe I can try to...
You have to measure it in Zeldins.
I always want something.
Maybe I can try to make my vote. So it depends on what you are measuring. So if you are, or it depends on what you are comparing. So if you are comparing, but when phasing or when building your model from one data set or from one list of intensities, like in traditional crystallography, and compare this to, and you want to know how well does your model agree with your data, then, and you measure you measure precision in this case, you're not really measuring accuracy, but maybe something close. You can use the R free factor, but R factors are not assuming the right distribution in R, in my mind. So you should be using at least something like the R factor, just using the correlation coefficient, something like the CC free or I don't know, or CC star or something like this. I don't know how they are called. So you make the correlation of what you would predict of the intensities to intensities that you have left out of the refinement and the model building, and look at how well do they correlate. This would be something very good in my opinion.
That's what R3 is.
But no, R3 is comparing the absolute differences between intensities. And this is not...
So you don't have intensities anymore by the time we're at the model,
CC free.
Yeah.
There's it's R crist, but R3 is a model, not a...
But it's still a cross-validation.
Yeah, well, it's a cross-validation tool, but I mean the model R and the R3 are different, like fundamentally different to like the R crist and R sim and stuff.
Tom White, you were going to say something?
Yeah, I was going to respond with a question to Oliver, which was, do you think this question about post-refinement always increasing the CC, do you think that still stands even when you do this by splitting the data at the beginning? So you take your data at the image level, you split it in two completely separate parts, and you run the whole post-refinement, whatever you like, completely independently on these two halves, and then measure that. Does that criticism still...
So we talked about inside the Gordon, right? But that's measuring something different. So what you're saying is, here's all my data up here. I can calculate CC1/2 of everything. But what you're saying is, let's split it into two here. Yeah?
Yeah.
Post-refine these two, and then cross-correlate these two. Now, I think that that's actually measuring the variance of your post-refinement scheme, not the CC1/2 of your data. Yeah.
You should do it at the HKL level.
Well, what I suggest one should do for CC1/2 is take your your Miller space, so all the possible Miller indices, take out a cross-validation set, post-refine on all the intensities which aren't part of that set, and then look at the CC1/2 within the cross-validation set.
So all the HKLs.
Yeah.
So you, from the outset, would declare your free R flags.
Actually, I've been collaborating with some guys in the computer science and statistics department at Stanford, and I went to them with my cool new scheme, and I said, "Oh, look, the CC1/2 gets better." And so the guy asked me, "So what is this?" And I explained it to him, and then his face, it goes, because of this target problem, which is different to the rotation thing, to be clear. But his face goes like this, and he told me to come back when I have cross-validation.
Okay, I think we should...
Can I ask,
of course.
what does the rest of the panel think about using intensity statistics? So the NZ test, the L test, based on these are based on Wilson statistics. It says that the E values should form a Wilson distribution or an exponential distribution. So if you just look at your merged structure factors and ask
If they have this distribution, we get a big difference.
whether we've applied a partiality correction or not.
Yeah, they are possible. I think, but not the gold standard. I think they are more to find errors in the indexing there, yeah.
Well, not only in errors in indexing, but better algorithms for integrating and merging.
Does it do that with my fake data?
Well, so your fake, yeah, but your fake data, I can either do the refinement of the angles or not, and if I do so, I get better L statistics.
You do?
Yes, absolutely.
So let me go back to the question I asked earlier. To do that refinement, you have to scale all your data together on a common scale. You said, oh, well, I use a standard. And you said you justified that because you just want to find out how best to do it. I accept that. But normally, you don't have a standard. What do you do then? My guess is what you would do then, you don't have a standard. You scale everything against everything else. And then that gives you your first refinement iteration. And so for the next refinement iteration, you've got a new set of maybe slightly better relative structure amplitudes. Then you do your post-refinement gain. Is that how you see it in the future? Rather than, one would not normally have that absolute standard which you've got used for your testing of your methods.
Generally, yes, I'd agree, but you can refine the orientation simply based on how far your predicted spots are from the Ewald sphere. That's the first thing you can do without any intensity.
Yes, I quite agree, and that works quite well. Yeah.
You can only go so far with that.
Yeah, I agree.
And after that, yes, you'd have to look at the intensity.
Yeah, I've actually been doing that with some virus data. Yeah.
I think it's important to note that that scheme fundamentally assumes that your data come from a single population.
Data is a single population. What do you mean by that?
What I mean is that because you're using
two non-isomorphous crystals in the mix.
Oh, I see. Yeah, you're dealing. Yes, sure. They all belong to the same data set. Well, if you're doing things like time resolved data, then you've got to have a problem of that sort, where you want to sort out the different times, which is an interesting problem.
Again, about the Wilson statistics, I think they are a good tool, but they are not as robust to random errors. So if you have much data to compare and you can do much of this statistics, of course it has to follow this statistic, but they are not as robust.
As what?
As the correlation coefficient to an external reference, for example.
So the correlation reference is correlated to the target function of any kind of optimization.
Yeah, if you had an external reference, for example. If you have an external reference and make the correlation coefficient, nothing can be, or nearly nothing can be more robust.
Well, yeah.
Okay. To answer Nadia's question, I don't think there's ever going to be a single number that lets you come to any conclusion you want. Just scientifically, at this stage in the game, if you're using the software and stuff, I think come up with controls. A lot of your biologists, you're used to dealing with a system that you don't really understand, and that the rules can keep changing and stuff. So you have to come up with your own test, your own controls for what you're looking for and what you're not looking for.
Or compatibility with the results of other methods and functionality of the protein. I mean, can you predict what it'll do on the strength of the density?
Compatibility with the desired results is a dangerous one.
Yeah.
That's why you have a negative control.
And on that note, I think it's dinner time.